Compressive sensing for wireless communication networks. Compressive sensing has been widely adopted in wireless communication networks as an effective technique to mitigate issues associated with traditional communication schemes. Wireless communication networks use the transmission of analog signals through the propagation medium, which is often an electrical or electromagnetic field. The transmitted signal is often interfere by noise and signal distortion as it traverses through the propagation medium. Moreover, the rate at which data is transmitted across the network is limited by the channel capacity and the bandwidth, which are constrained resources. Compressive sensing is a technique that utilizes the intrinsic structure of the signal to transmit a similar amount of information using a less amount of data. Compressive sensing works by exploiting the intrinsic sparsity of the transmitted signal. A signal is sparse if it has only a few non-zero coefficients in a well-defined basis. For example, an image C and be sparse in the wavelet domain if most of its coefficients in a particular wavelet basis are zero. Compressive sensing techniques take advantage of this sparsity property and reconstruct the sign with fewer measurements than traditional methods. One of the key advantages of compressive sensing is its ability to enable sparse signal reconstruction with a small number of randomly selected measurements. This is due to the fact that compressive sensing is based on the principle of incoherence and randomness, which ensures that the random measurements preserve the essential features of the signal. In wireless communication networks, compressive sensing techniques are used to reduce the amount of data that needs to be transmitted across the network. The traditional communication schemes require that the entire signal be transmitted to the receiver, regardless of the sparsity of the signal. Compressive sensing, on the other hand, allows for the transmission of only a small fraction of the entire signal, thus reducing the amount of data that needs to be transmitted. This reduces the bandwidth requirement and, therefore, results in increased network efficiency and decreased transmission cost. Another application of compressive sensing in wireless communication networks is in the recovery of signals from sparse measurements. In traditional communication schemes, the signal is first digitized and sampled and then transmitted across the network. The receiver then uses a decoder to convert the signal back to its original form. The decoder requires a large number of samples to be able to accurately reconstruct the signal. In contrast, compressive sensing techniques utilize the intrinsic sparsity of the signal to recover the entire signal from a low number of measurements. This results in a more efficient and cost-effective signal recovery process. Furthermore, compressive sensing allows wireless communication networks to utilize the sparsity of neighboring signals to further enhance the efficiency of the network. This technique is called distributed compressive sensing. In distributed compressive sensing, the sparse signals from individual nodes in the network are collected and transmitted to a central location for signal reconstruction. The central location then uses compressive sensing techniques to exploit the sparsity of the aggregated signal and reconstruct the original signal. Moreover, the use of compressive sensing is not limited to wireless communication networks. It has found numerous applications in other fields such as medical imaging, radar, and astronomy, among others. In medical imaging, compressive sensing has been used to reduce the amount of data needed to acquire an accurate image, thus reducing the radiation dose required for patients. Similarly, in radar In astronomy, compressive sensing has been used to improve the quality of the acquired data while reducing the power and data storage requirements. In addition to its wide applicability, compressive sensing has also led to the development of new mathematical tools and algorithms. These tools have enabled the efficient implementation of compressive phase sensing techniques and have paved the way for further research in the field. Despite its numerous advantages, compressive sensing is not without its limitations. One of the main challenges in compressive sensing is the design of the measurement matrix. The quality of the varied signal depends heavily on the properties of the measurement matrix, such as its incoherence and sparsity. Moreover, the design of the measurement matrix can be computationally expensive, especially for large-scale applications. Another challenge in compressive sensing is the impact of noise on the reconstructed signal. Compressive sensing techniques are inherently robust to noise, but the presence of noise can still impact the accuracy of the recovered signal. Therefore, the development of robust compressive sensing techniques that can accurately recover signals in the presence of noise remains an active area of research. The impact of compressive sensing is significant and has revolutionized the field of signal processing. Its ability to efficiently recover signals using a small number of measurements has opened up new opportunities for a wide range of applications. One area that has been particularly impacted by compressive sensing is imaging. Compressive sensing has enabled imaging using fewer measurements, It has led to the development of new imaging systems with improved resolution and reduced costs. An example of an imaging system that has been developed using compressive sensing techniques is the camera pill. The camera pill is a medical device that is used for endoscopy and colonoscopy procedures. The camera pill is swallowed by the patient, and as it travels through the digestive system, it captures images of the internal organs. These images are transmitted wirelessly to an external device, safe for processing and analysis. The camera pill is an example of how compressive sensing is being used to improve the efficiency and cost-effectiveness of medical imaging systems. Another area that has benefited greatly from compressive sensing is remote sensing. Remote sensing is a technique that allows the measurement of physical properties of the Earth from a distance. This technique is used for numerous applications such as climate modeling, disaster management, and resource management. Compressive sensing has been used to improve the efficiency of remote sensing systems by reducing the amount of data that needs to be transmitted and processed. For example, in climate modeling, remote sensing is used to measure various physical properties of the Earth such as temperature, rainfall, and humidity. These measurements are used to develop accurate models of the Earth's climate. However, remote sensing systems generate a large amount of data, which can be challenging to process and transmit. Compressive sensing has been used to reduce the amount of data that needs to be transmitted and processed, thus improving the efficiency of the system. In addition to its impact on remote sensing and imaging, compressive sensing has also been used in other applications such as speech recognition, video processing, and bioinformatics. Compressive sensing techniques have been used to improve the accuracy and efficiency of these systems, thus paving the way for new advancements in these fields. In speech recognition, Compressive sensing has been used to reduce the amount of data needed to recognize speech accurately. Speech recognition systems generate a large amount of data, which can be computationally expensive to process and analyze. Compressive sensing has been used to reduce the amount of data needed to accurately recognize speech, thus improving the efficiency of these systems. Similarly, in video processing, compressive sensing has been used to improve the efficiency of video compression algorithms. Video compression algorithms are used to reduce the amount of data needed to store and transmit video content. Compressive sensing has been used to improve the accuracy of these algorithms, thus reducing the amount of data needed to achieve a high-quality video. In bioinformatics, compressive sensing has been used to analyze biological data. Biological data is often high-dimensional and complex, which can make it challenging to analyze. Compressive sensing has been used to reduce the dimensionality of the data, thus improving the efficiency of the analysis. Thanks for watching.